Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is Lesson 4, Writing Products as Sums and Sums as Products. So, classwork example 1, this is the distributive product. I'm not going to take time to do arrays anymore, for this is the width and this is the length. But keep in mind that's the process, and we are distributing. 2 times x is 2x. Positive times a positive is positive. 2 times 5 is 10. 3 times x, 3x. Positive times a positive, positive. 3 times 4, 12. 6 times x, x. Positive times a positive. 6 times 1, 6. 7 times x, 7x. Positive times a negative, negative. 7 times 3, 21. Okay? These are not like terms. An x coefficient times an x plus a constant. We cannot add these and say it's 12x. No, this is not 15x. This is not 12x. Okay, we cannot combine them if they aren't both like terms. I would need an x over here to take 7x minus 21 and get negative 14x. Right now it's just simply 7x minus 21. Okay, now we're going to work backwards. And to go from standard form to a form where we know the width and the length, if you will, it's called factoring. Okay, so you have to ask yourself, what does 5 and 30 have in common? What factors? So 5 is prime. So the factors of 5 are 1 times 5, and the factors of 30 are 1 times 30, 2 times 15, 3 times 10, 5 times 6. Okay, factors they have in common are 5. So I'm going to factor out a 5. 5 divided by 5x divided by 5 is simply 1x or x. Positive divided by a positive is positive. 30 divided by 5 is 6. Okay. So notice what's going on here. If you can't do this in your head and you do tables and factors, okay, notice that this would represent my x's here. And if I factor out a 5, that's how many x's I have left. I have 1x right here. And then if this is the number 30, constant 30, factors out a 5, then it's leaving the 6. And that's what's here. 5 times 6. Okay, so it's just factor. So I see an 8x, I see an 8. That one's easy. I know 8 will go into 8, and 8 will go into 8. If I take 8x divided by 8, I'm left with x. Plus 8 divided by 8, 1. Okay. So if I distribute these now, 8 times x is 8x, 8 times 1 is 8. So we can go back and forth and check after we're done. Okay, this one's a 3, this is a 12. 3 will go into 12, so 3 goes into 3 and 12, so I factor out a 3. 3x divided by 3 is x. 9s, careful with that sign. 12 divided by 3 is 4. Okay, h, 15 and 20. Okay, so if I did a factor table or factor 15, it'd be 1 times 15. 2 times, doesn't work. 3 times 5. Okay. I want to go back though and revisit Euclid's algorithm. Euclid's algorithm simply states that if you take two numbers, what is the greatest common factor of 15 and 20, and I divide 20 by 15, I do this, and when I subtract, I get 5. I do this until I don't have a remainder, and that will find my greatest common factor. So now I'm going to take 15 and divide it by my remainder. And 3 times 5 is 15. Subtracting gets 0. There's my remainder of 0. Do you remember this rule? It's really cool because once I realize that I have no remainder, this divisor is my greatest common factor. So I'm going to factor out a 5. 15 divided by 5 is 3x plus 20 divided by 5. Okay, so there's another visit to Euclid's. I actually really dig that. So if let's go back and do one of these with you. Here's 30 and 5. So if I take 30 divided by 5, 6 times 5 is 30. Subtract, I got a remainder 0, so 5 is my GCF, and 5 is what I got. Okay? Exercise 1. Rewrite the expression as a product of two factors. Okay? Again, if I use Euclid's algorithm and I divide 72 by 8, 9 times 8 is 72. Subtract, I have no remainder, therefore 8 is my greatest common factor. So I can take that out. And I'm just setting this up, and 72 divided by 8 is 9. 8 divided by 8 is 1. So it's 8 times 19 plus 1. Okay, this one's easy. 36 goes into 72. 36 is half of 72, so I can factor out 36, leaving z plus 36 times 2 is 72. Okay, 3. Obviously, 3 can be factored out, leaving r plus s. Okay. Euclid's algorithm on this one. 55, the bigger number divided by the smaller. 5 times 11 is definitely 55. I have a remainder 0, so there's my GCF. So I'm going to factor out 11. And 55 divided by 11 is 5. A plus. Okay, 15 and 144. Great example of using Euclid's algorithm here because I know 15 will not go into 144 evenly. And 10 times would be 150, so I'm going to go with 9. 9 times 5 is 45. 9 times 1 is 9, plus 4 is 13. Subtract 44 minus 35 is 9. Take what I ended up with, my remainder, and divide my old divisor by remainder. 1 times 9 is 9. 15 minus 9 is 6. Take my old 9. Now I'm going to divide it by my remainder. 1 times 6 is 6. Subtract and get 3. Finally, when I take that 3 and divide 6 by it, I get 2 times 3 is 6. Subtract and get 0. This is my greatest common factor. So I factor out a 3. 144 divided by 3. 3 goes into 14. 4 times. 12, 2, 24, 8 times 3 is 24, Q, minus 15 divided by 3 is 5, Bazinga, it's 3 times 48 Q minus 5. Okay, example 2. Let the variables x and y stand for positive integers, and let 2x plus 12y and 8 represent the area of 3 regions in the array. Determine the length and width of each rectangle if the width is the same for each triangle. Sorry, for each rectangle. The width is the same. Okay? Okay, so what are we going to do here? We need to factor. Okay, so remember we're factoring out. What will 2, 12, and 8 all have common factors of? Okay, even, so I would say 2. 2 times what is 2x? 2 times x is 2x. 12 divided by 2 is 6, and we have that y. And 8 divided by 2 is 4. Okay. So the length and width of each rectangle. So the length of this rectangle is x, the width was 2. The length of this rectangle is 6y, the width was 2. The length of this rectangle is 4, the width is 2. Okay. Exercise 2. Write the product and sum of the expressions being represented in the rectangular. Okay, so we're taking the width times the length. Okay. So that's one way. Or I could just take what's already been done in here and put plus signs in between. Which is 24D plus 8E plus 6. Okay, so that's product and sum of expressions being represented in the rectangle. Either way. Okay. B. Factor 48J plus 60K plus 24. Find the greatest common factor of the terms. Since I have 3, I'm going to do factor trees. So I'm going to take 48, which is 2 times 24, which is 2 times 12, which is 2 times 6, which is 2 times 3. So that's 2 to the 4th times 3. Now I'm going to do 60, which is 2 times 30, which is 2 times 15, which is 3 times 5. So that's 2 squared times 3 times 5. Okay, prime factorization. And now we're going to do 24. 2 times 12. 2 times 6. 2 times 3 gives me 2 to the 3rd times 3. I want everything in common from each one. This has a 5, but no one else does. This has a 3. This has a 3. And this has a 3. So that is part of the prime factorization. That is in common. This has 2 2's. This one has 3, and this one has 4. So I can represent 2 to the 4th as 2 squared times 2 squared, and 2 squared is here, and then 2 cubed is 2 squared times 2 to the 1. Okay, so if I take the common portion of all these, it's 2 squared. So I have 2 squared, which is 4, and I have a 3. All 3 of them. They all have 2 squared, and they all have a 3. Okay, so these are my 2 common components. Okay, 2 squared is 4 times 3 is 12, so that means I can factor out a 12. 48 divided by 12 is 4J, plus 60 divided by 12 is 5. Okay, and notice what's left over. 2 squared is what goes inside. What's left over, 5, is what is here. And what was left over here was a 2 to the 1. 24 divided by 12 is definitely 2. Okay, so the factor trees actually tell you your commonality and your differences are what go inside your parentheses. Really try practice doing several of these over and over and over until you understand that concept. It will pay you back tenfold in the years to come. That's the end of lesson 4. Go for your problems.